Let's see if we can talk a little bit about angular momentum today. Oh my goodness, we don't need this. We need this. Let's see here. Okay, so we're going to take a look at, let me move this a little bit. Whoops. Make full screen here. All right, so we're looking at angular momentum. By the way, I just updated this yesterday, and I'm going to put this in the new version. There's two ways to calculate the angular momentum. This is the way we talked about. I used our conversation yesterday to try and clean up the notes, so I made it a little prettier. For extended objects, we use I omega. When we've got this perpendicular distance, we called r perp. Remember this all day. We can call that the impact parameter. Here's another trick that maybe you saw or maybe you've thought of. I forgot that sometimes students discover this on their own, so I decided to throw it in here. Look at this clever way of doing it. You can actually use this distance right here, and then you could use this velocity that is perpendicular. So you either use the radius that's perpendicular or the velocity that's perpendicular. So notice you could use v perp, and this is a cool way to do it as opposed to using the radius. Oh, whoops, sorry, you could use the perpendicular radius and then the full velocity. So you could basically say use one of these things and then find the other one, which part is perpendicular to it. Where is that coming from? That's coming from this cross product here, if I can get the right thing. Because we have an R cross V, mass is a scalar, it just pops out. You either take the perpendicular portion, the amount of this perpendicular to that, or that perpendicular to this. All right, so that's a new style. If you're into that, that's cool. Let's go ahead and scroll down here. All right, that's cool. The rest of this is all the same. And I think last time we left off at 11.9. So we talked about this one last time, and hopefully you guys were able to finish that one up and do that one. And then I think we talked briefly about this, and I sent you some cool videos. So now I want to look at this information here, all right? Deep thoughts. All right. So this is something I expect you to know, and perhaps it will show up on a test, okay? So you should know this fact. In free space, an object tends to rotate about the system's center mass, okay? In free space, both linear and angular momentum are conserved as long as you have no pivot. And this is what we just discovered. So this was what we discovered in that problem 11.9. If there's no pivot, you get both P initial equals P final and L initial equals L final. All right, that's cool. Next. When you do have a pivot, the object rotates. And then watch out, remember this, for an object swinging in a circular arc, gravitational relates to the center of mass radius. This part right here is the part you gotta, it's usually easiest in a problem for a swinging collision to find the center of mass position and then calculate MGH on that. And then finally, this is a neat fact. Collisions involving rotation and translation, generally speaking, this is not always true, they generally tend to lose less energy compared to translation only. Let me give you an example of that. All right, so I'm going to put something on here. If you have a rod here and a similar rod here, okay, and then we come at this thing, if you have a ball that's going straight at the center versus a ball that's going over here, and if I could make this clear with an arrow, this one's basically going to hit right at the center of this thing. It's not going to rotate. Whereas this one, if it hits, When this one hits, the center of mass maybe is going to be, whoops, the center of mass might be right about there. The center of mass is going to translate, and because this one's hitting way up here, it's also going to rotate about that center of mass. And so this one, when it hits, it's only going to translate because the center mass is right in the center. So it turns out if you hit something off center, the act of having the rod has to give during the collision a little bit, and you actually lose less energy that way. And so this is a weird scenario. These two actually will have the same translational momentum afterwards. So let's say this V final equals 6 meters per second after all is said and done, right? The conservation of momentum problem is exactly the same. This one would also have 6 meters per second after the collision, but it's also going to have omega. And notice you have some amount of energy initial, 1/2 mv squared, right? And that's going to be the same 1/2 mv squared in either case. You have the same initial energy. Because this one has more final energy, it means it lost less. And just in case that lags, I want to say that again. Because we have more rotational energy in this one, we have more final energy. That means you lost less. So that's what I was trying to get at with this point right here. That's what I was trying to say right here. Okay, so that's kind of our thoughts about, we talked about collisions. If you have a pivot, do angular momentum. If there's no pivot, do both angular momentum and linear momentum. Watch out, if this thing has a pivot and it's swinging up, watch out for this gravitational potential energy, use the center mass, and usually don't get freaked out if you have a collision that has rotation, if it loses less energy than you expect for a translation only. All right, so this is an old test question I gave. Let's take a look at it. All right, so you have a space probe. It's rotating, okay, solid disk, radius r, and there's an antenna that has length 2r. Got it. So that means this radius right here is r. And this whole thing is 2r. Got it. The probe is slowly rotating at this. The probe then extends its signal to Earth. When the antenna is extended, it's at the, okay, so that's right here. It says the mass of the antenna is equal to the mass of the rest of the probe. All right. So there's all our stuff. Let's think. Should we do an energy problem, angular momentum problem? What do you think? Discuss with yourself. Or yeah, think to yourself. Should we do energy or angular momentum to analyze before and after? Let me see here. Got it. Okay. So Trey just showed up right on here. That's cool. And then I don't know what the two spools demo is, so I'm not sure there. It might be. Yes, it is, Ryan. Yes, I think you're right, if I remember what you're talking about. Okay, so hopefully what you thought was L initial equals L final. All right. And if you try to use energy, energy may not be conserved in these problems. I hope you've seen that. Now think about it. Energy might be changing. I don't know if it's going to go up or down, but there's some battery inside this stupid device. And that battery is converting chemical potential energy, and it's doing work on the antenna to move it. So in this problem, there's a weird source of energy. It's maybe a nuclear power or whatever source, and that's causing this thing to move out. So we don't know how that energy will affect the final and initial rotational energies, all right? So what is the initial moment of inertia before it has extended? So I think that's not too bad. It's going to be I total equals I1 plus I2. And if you have any questions, dump them in the chat now that Trey's here. Just keep them coming. He's been doing a great job all semester. We really appreciate his help. So in this case, I1 is a disk. So that's going to be 1/2. And then this one is going to be a 1/12 because it's a rod at the center. But look out, the rod length is 2R. So let's go over to the solution and take a look, because that's faster than me writing all that. So again, I'm doing part B. What is the initial moment of inertia? All right, so that should be right here. Oops. There we go. So looks like I said a bunch of boring words there. I think we've already said all that. So I rod at the center and I disk at the center. So I get a 1/12 ml squared. But remember this L, don't forget, L, the length, equals 2R. Okay. All right. So there's that. Not too crazy. Let's go back and look at the other one. All right. We're looking at the center of mass. After the antenna is extended, where's the center of mass after the antenna is extended? Well, I know this one here is right there. I know this one here is right there. And because they have the same mass and they're the same distance away, hopefully you agree, the center mass should be right here at the edge, right? Again, X center mass is X1, M1 plus X2, M2, etc. And here, these are both the same. This one's negative R, this one's positive R, so it's going to end up being 0. So I would call this X equals 0, or maybe you call it positive R, whatever, it doesn't matter. So let's clear all those and verify if there's anything in here. So that's at the edge of the disk. Hopefully that explains why. All right. And now let's go back and see the other one. Probably looks like the final moment of inertia. All right. So let's go back and look at that. Final moment of inertia after it's extended. So this one's going to be a little bit different. We need to know something. Where's the axis of rotation? Think. Where is the axis of rotation? This thing is in free space. And then, okay, so there, yep, it's at the center of mass. Sean, usually you would use a point mass. Usually, if you see lump of clay in my problems, usually you think of point mass. Okay, and so it's right here and then right here. So that puts the axis at the center of mass in free space. So this, the satellite was rotating about this point, and then after the antenna extends, it's going to rotate about this point. If you know anything about satellites or spaceship design, you would probably immediately think this is a very stupid design, because now the whole satellite's going to be whipping around instead of just whipping about its center. So this is probably putting greater force on the connections inside the satellite, but whatever, who cares? All right, so notice this is a tricky problem now. Let me get the chat here. Yep, okay, Trey's on it. Okay, so work with Trey on that, Sean. I'll stop talking. And then let's go ahead and look at this one here. Notice, I just want to point this out. You're going to have to do the parallel axis theorem for this one. It's shifted over by rod. So I of the disk is no longer 1/2 mr squared. It's I about the center of mass plus mass of the disk times the distance it's shifted squared. This, in this case, is capital R. All right, so you get an R squared. So now this is going to be 3/2 mr squared. And the rod is now at its end. So now it's 1/3 mass length squared. But the length of the rod is not r, it's 2r. And that's going to be squared. So what do we get? I think a 4/3 m r squared, if I did the math right. So then you have to add this to this. And so we're going to get something with 6 again. And let's go check that out. I'm going to pause for a second, make sure you got that. Okay, here we go. So notice we get 1/3. There's the parallel axis theorem. When you plug in all that stuff, that's what I got. All right, and let's go back to the other one. Now, what is the new rotation rate? Again, that was the point of part A. We're going to do angular momentum now. And I will get to the chat in a minute, just in case it's important. So here I did L initial equals L final. In this case, it's an object changing shape. So I'm going to say I initial omega initial equals I final omega. You got the I initial, you got the I final. We know omega initial. So in this case, I rearrange that for omega final. And so I just plug in the moments of inertia and you get this. Notice we didn't need to get it out of RPMs. So that's kind of cool. And then just to finish this before I get the chat, here's a way you could go ahead and calculate the change in energy. It's final energy minus initial, and it looks like you lost 70%. So this is actually a really dumb satellite design, all right? So, okay, cool. And then let's go back and take a look at the other parts here. I'm starting to myself. So percent change in energy, all right? That's what we just figured out. And what is doing work? The battery or the nuclear power source that is inside of here that's causing this rod to move outwards. If you think about it, think about the figure skater demo, right? This is the one where you're spinning around and you bring your arms in or out like this. When you do that, you know that when you bring your arms in, you speed up. Where did you get the energy to speed up? From the Snickers bar you ate for breakfast. So, right, when we ate that bowl full of Snickers bars and milk this morning, actually that sounds pretty good to me right now, but right, you get chemical potential energy. It's just like this satellite. There was a battery inside that moved your arm in or out, right? So you have chemistry going on inside your body, which is converting chemical potential energy. And so technically we could, in theory, try to compute that and use some averages from biological, and everybody's got a little bit different efficiency in the way they compute their sugars and stuff. But it's so hard to do the problem that way. You could, in theory, do an energy problem if you could account for the energy inside the motor and all that work being done, but that's way too hard. So why not do these types of problems with angular momentum? So if you see a collision and things rotate, use angular momentum, not energy. If you see something rotating and changing shape, use angular momentum, not energy. It doesn't mean you couldn't do it. It's just really freaking hard, and it would be a dumb way to do it when angular momentum, if you recognize it, is so easy. Comparatively, it's not easy, it's easier. All right. So let's go back to that question and see what else we've got in there. And you've probably got this in front of you. All right. So how does the period of the rotation rate change? Think to yourself. Try to answer these ones really quick. These were some conceptual questions I asked. All right. And just make sure you've got all of these things. This might surprise you, one or two of them. And then I'll go ahead and start going through them. If I'm going too fast, I apologize. If I'm going too slow, I also apologize. If I'm going just right, no apology. Okay. I'm losing it. This online crap kills me. Okay, how does the period of the rotation rate change? I think we saw I final is greater than I initial, which makes me think omega final should be less, right? If you're a figure skater and you bring your arms out, your moment of inertia goes up. If your moment of inertia goes up, your rotation rate. So now if rotation rate is inversely proportional to period, right? So in this case, that says the period final should be bigger, right? It rotates slowly. That means it takes more time. So I say the period should increase. How does the probe's angular momentum change? Hopefully you thought stays the same because we just used that fact to do the problem. Right? Remember we said L initial equals L final. So that was a trick question. Hopefully sometimes it's just, it doesn't change. Another way to say this is the sum of external torque. Do you remember me mentioning any external torque? We talked about a motor, which was inside the system. There's no external torque. If you have no external torque, that implies it stays the same. All right. How does the rotational kinetic energy change? Did we see anything there? Usually when this is true, we're going to say this is true. Not always, but in this case, we did the math and that was true. You can actually do the math right here and we saw that it lost 70%. Okay. How about the translational kinetic energy? I'll let you think for a second. No change. Isn't that wild? So here, there was no external work done to change the translational kinetic energy, right? We did account for this rotational change, but if this thing's flying along and there's no force exerted on it, the force external equals 0, which tells us that A is equal to 0, which tells us V equals constant. And there, since the velocity is constant, that tells us K is also constant. So that's kind of funky. So what will happen to this satellite, it's going to be whipping along through space, rotating, and then the antenna is going to stick out. It's going to keep rotating, but at a slower rate, and it's going to keep translating at the same rate. And then hopefully here, you said it was at the center of mass. All right, and I'm going to clear all this and check the chat. Okay. You might be right, Sean. I have no idea. I lost where I was at there. Sorry about that. It's so goofy trying to get your feedback on these. So I guess I got lazy and just, I'm assuming you're thinking about it, and I hope that's good enough. So my apologies if I didn't respond in a time sensitive way. All right. Whoa, I forget where I'm at now. All right, any questions right now while I get back to the right page here in my book? I think we just did 11.11. Yeah. All right. Doing all right? And then, okay, cool. Let's take a look at this next problem here. This is one of my favorites. Mad props to Alexis R, who just found a typo in it, and I fixed it up in the solution. 11 point nasty. All right. So I'm going to be straight with you. This problem is nasty, but the setup for it is totally good practice. So I just want to point out the following here. Look at these notes in here.
This happens to be one of the harder problems I've solved in the book. Okay, if not the hardest. Okay, but if you get stuck, the first page of the solution has a hint. And this part I want to tell you, okay, this is easy for everybody. Not easy, but doable. This is doable for everyone. This part right here. Solving it all the way through, debatable whether that's worth it. I'm insane. I wanted to do it, so I did it. Alexis did it as well and found my typo. So you got to give him mad props, all right? So I missed a factor of 2, and then it's in some long thing. But it's actually a really good problem. And the year I assigned this, I ended up just sticking it straight on the test, but upside down to see who would actually do all the work. And it was pretty obvious. So I'm just telling you right now, if you do this, you're a lot stronger student. I'm going to show you. Let's see what the chat says here. Yeah, Nate Dog, have a blast. All right. I'm going to go ahead and just give you a taste of what this solution looks like and where you might want to stop. Okay. So, all right. So this is 11.111. So this is the hint. And then, so if you get stuck, look at the hint. And then I kind of walk through, all this is good. 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 Right here, it starts to get, yeah. So from right here on, you end up having to do a quadratic. So once you quadratic, that's where I would bail on this problem. Because when you look, it just starts to get crazier and crazier and crazier and crazier. But if you want, I just redid it. Alexis, you could double check if I did it right. All right. Okay. Yeah, it's totally horrible. But look, this last page is horrible. But this page is totally reasonable. By the way, I got this problem out of a book. And then all I did was I changed which variable was unknown. I got this out of Halliday and Resnick. This is a classic physics problem. Now, what Halliday and Resnick does is it makes you solve for omega, which is slightly easier. Solving for M1 is a lot harder. So if you can do this and get this problem done and at least write all the appropriate equations, that's what matters. Solving it all the way doesn't matter, but getting the equations matters. That shows you're competent. If you can't do this, that shows you aren't competent yet. All right. And so you've got to make sure you do this one. Right. You'd be crazy not to. Look at everything it does. There's center of mass, there's parallel axis theorem, there's momentum, there's lever arms, there's energy. I mean, this is really where you need to be for the final. So you're crazy if you don't do it. Yeah. All right. But again, to be clear, on 11-point nasty, if you hit the quadratic, just stop the madness because you have done the equations. But if you can't do all that setup, it's like, it's a really good review of everything you need to know. So I think it'd be insane not to do it. I'm going to let you struggle with it. Good. All right. So let's take a look at page 90 really quick. So page 90 and page 91. Now, we are not, whoops, where's that document I want here? Now, we unfortunately do not have class today in person, so I can't show you this cool thing in person. But what I did, let me see if I can just copy this. I'm going to see if this pastes in here. So I have a link here in the you could watch this afterwards. Maybe you could copy this to your thing and watch the demonstration of Veritasium later. It's a really cool video. So I can't do that demo with you live. So there's a video for it. If you look at page 91, there's another one. So let me get that one in here. And I just want to point out the words. This is about the magic wheel. It talks about pre-session, not pro-session, pre-session. And there's the other link to that video. So you've got a couple of videos there. Maybe I was hoping what you could do is check those out, maybe copy and paste those onto a document so you could watch them after class or something. Oh, did I reference Star Wars? Oh, shit, I did. Oh, is this being live streamed? I said ship. The lag really changes things sometimes. All right. So, yeah, you could try that one out. And I put a lot of effort into those figures. So what you might do is maybe watch the videos first and kind of get a feeling for the objects moving. And then if you read through these solutions, there's some of the coolest demos ever. And we'll do them next time we're in class or something, maybe in fall when school starts up or something, if we get that going. So that said, that's cool. Oh my gosh. This is a really fun one too. Look at page 92, everybody. You guys are really missing out, not getting lecture, but I'm going to try and share my screen for a second. This one is crazy. I got to say something about this one. Look at 11.14. There's those. So whoops, 11.14. I want this one, I think. Come on. Oh, whoops. So that's that one. Cool. Chewbacca-ness. Cool. This one's fun. Yeah, anyways. All right. So normally this is a demo we do. I'm just going to leave it this way. It relates to this one. So I'll just show you the solution. It's kind of hilarious to me. Back in the day, I used to make students do things. Look at this suitcase. So I had a student, Alex Valenzuela. He's now working in the community, and you never know, he might be your boss someday. So remember this secret suitcase, okay? Just in case you get a job interview with Alex. He put this 45-pound weight in here. Look at this stupid thing. This is amazing. And so what you would do is we'd get this wheel inside the suitcase and we would spin it up with a Dremel tool, hide it outside and spin this up to rapid speed. And then what happens is if you walk, it's got so much angular momentum. If you try to turn, the suitcase will turn because it's got so much angular momentum. It's insane, right? So this is basically called a flywheel. It's a wheel. And once you get it going, it's extremely difficult to change the rotational state. And when you do that, if you try to turn, it feels like it jerks your arm out of your socket. And whether it's true or not, I do know that Linda Metaxas did this demo one day, and then she was in the hospital for the next 3 days. So was it physics? We'll never know. Anyways, but yeah, I think it was actually just a random heart condition, but she got better. Yeah. Oh, that's cool. So yeah, so Nick, are you talking about the flywheel? Looks like Nick S threw one in the chat. Yeah, so that's pretty cool. Right on. I'll have to check that out. I'm going to copy that and look at it later. I'm going to get a document going in case the chat goes away from me. Just saving that for me for later. Okay. All right. Good. Let's see. Hey, riding a bike. This is a good question to think about. Try and answer this one yourself, 11.15. See if you can use these conceptual problems to, after you kind of watch those videos, see if you can understand why it's easier. Or think of this another way. Why is it easier to balance a basketball on your finger when it's spinning or a book, right? Like if you try to balance a book on your finger, it's pretty hard, but if you spin it, it's a little bit easier. So you could think about that as well. All right, next, 11.16, and I want to point out some stuff that Alexis found for me, all right? So Alexis he's just rocking it right now. Mad props to Alexis. Oops. All right. Oh, whoops, that's the solution. I want the question. All right, this is a great question, everybody. You got to do 11.16, and you got to be careful here. And the typo that Alexis found, he found 2 of them. In your book, look careful. In your book, there was a 2 there. I think that needs to be gone. Okay. So no 2. So scratch out the 2 in your book. And then just to be clear, I want to be clear that this is angular acceleration magnitude. I didn't say that, but I think I meant it. All right. I want this to be angular acceleration magnitude. All right. And then make those corrections in your workbook right now if you've got it. All right. And I'm going to see if Alexis has anything else in the chat. Yes, Jay, we tried to make students actually turn the suitcase. And so we would spin it up and hide it from them behind the desk. And then I'm saying, all you got to do is take that suitcase and take 3 steps forward and then turn and try and slide it into the box so the bomb doesn't explode and kill us all or something, right? Because we said, pretend you're in an airport and you discover there's a bomb in the suitcase and you need to throw it in the bomb box or something. Yeah, that's what we used to do. It was kind of fun. All right. So I'm taking, I don't know if that's sarcasm, Nate Dogg, or not, but yeah, okay, whatever. That's cool. All right. So everybody, I want you to do this problem at home. And the most common people miss, you might, if you've got your book, you might underline that of the person right now in part C. Okay. Underline that of the person, part C. I might let you guys do that one at home. Normally, this is one I do in class and take some time. You know what? We're trying to learn right now, right? As strange as this sounds, I think what maybe we should do is, why don't you try to do 11.16 right now, and I'll just stay on the line. And maybe what I'll do is I'll see if I can figure out how to delete the boring next 20 minutes. I want you guys to actually try 11.16 right now. And then I'm going to try and answer the questions you come up with. Let me do one more thing here, and then I'll get to the chat, okay? So it looks like you should be able to do at least parts A through E. All right, that's straightforward. All right, so let's go take a look. Okay, there we go. All right, I have no idea what's going on. All right, so let's take a look at 11.16 and see how you're doing. All right. So I know it seems a little crazy, but we got to do some problems sometime. Why not now? So my thought was we'll just let you take a look at it and then we'll discuss the solutions as a group, but it's detailed enough. I want to give you a minute to try and wrap your brain around it. All right. So take a second, do the best you can, pretend it's like a quiz, but it's not, but just pretend it is and see how far you get. And yeah, if you want, when you're making the plot, if you get that far, you could try and just plug it into Excel and make a quick plot. And I would get in that habit of just using Excel to make your plots. All right. And if you've already done this one, you could always try and do 11.17. I'm going to find a problem that relates to 11.17, just so I've got it for you guys. kind of weird just sitting here doing nothing. If anybody has a question, definitely shout out. How are you doing, Trey?
I'm doing okay.
So there's an interesting technology that's used in some outer space technology for a power supply, which you might find interesting. And I think you would understand this. I don't know where you're at in class, but what they'll do is they'll take some nuclear material and they'll stick it next to a Stirling engine. Do you know what a Stirling engine is?
Um,
Have you done thermo?
we have a test on it on Friday, and
Yeah.
me not knowing what a Stirling engine should kind of give you a hint as to how it's going. We went over a few different engines though.
Yeah. So like you probably talked about Carnot first, and then
Yes.
from there, which Carnot is what, 2 adiabats, 2 isotherms, is that right?
Yes.
And so the Stirling is I think it might be 2 isotherms and 2 isovolumetrics or something like that. You could look up a Stirling engine. It's not the most common one, but it's a very cool engine. Yeah. So and then the idea is you stick this, the Stirling engine is one of the closest to the Carnot engine in terms of efficiency, but it's not an easy one to do calculations on. So, but you could check that one out if you're bored. I thought
Okay.
you might get a kick out of that because that's what I was thinking about during the satellite. Yeah, Nate Dogg, they're pretty cool.
Oh, yeah, I'm definitely gonna be spending a lot of time on Khan Academy for thermo these next 2 days.
I got you. I don't. Yeah, what's are you guys doing a lot of heat engine stuff or not really?
We did a little bit.
But that's not the focus.
Yeah, we did. I don't know. It's
And-
kind of been. It's been a lot to try and figure everything out, I guess. He was trying to figure out how to relate it to quantum physics, and then kind of quick overviews on the different, I guess, yeah, a few different engines and just heat cycles in general, and a few other things.
I got you. So you probably did thermal expansion, and then you probably did Q equals MC delta T, then PV equals nRT, and then heat engines, and then, yeah, I don't know. My workbook, do you have my workbook for that one, 162 workbook?
I don't think so. I don't think they have it anymore.
All right. Yeah, so I can get you a copy of that one if you want.
Okay.
Let's try and do that at the end of class. I don't know if it's any good, but I've solved a bunch of problems and I did the gory details for some parts.
Okay.
And so some parts of that workbook are better than others, but man, I worked the hell out of thermo. So you might want to talk to me about that. All right.
Yeah, sounds good.
All right. So we'll look afterwards and hopefully that's good. All right. So I'm going to go ahead. Hopefully you've had time to look at this. I'm not getting any questions. Maybe it's because I'm just chit chatting. So I don't want to just waste your time. I'm going to try and go through that solution. Hopefully you had enough time to at least attack it. All right. So my apologies if this was a dumb idea. You could tell me afterwards if having 5 minutes to work was worth it. I see this question and I know you may not see this, but I see an object that's rotating and it changes shape. That's what I see. I think figure skater bringing their arms out. This is a weird figure skater where it's a turntable and a person, but it's basically a rotating body that's mass distribution is changing. So I think immediately L initial equals L final. Now, to be clear, I've been a little bit lazy today. I want to remind you that L initial and L final are vectors. In this case, when everything's rotating the same way, those are the times that we can drop this. And I think for the problems that we've been doing, for objects that rotate and change shape, we almost always have it not reversing direction. So I don't know if it's possible for something to reverse direction like that. Maybe there's a way it can be done. I haven't thought it through, but I think for the most part, it's always going to look like this. And so we get the initial moment of inertia and then the final moment of inertia. Notice this important fact. And so this gets to Sean's question from earlier. Assume the person is a point mass. if you're not sure if it's a point mass, you can ask. During the final exam, I'll be sitting there in my Zoom room or answering emails again. So if you're not sure on a test question if something is a point mass or not, just ask. Typically, lumps of clay are point masses. And while not usually true, you wouldn't think of this person as a point mass. As they walk outwards, it turns out within a few steps, they actually do act like a point mass. And if you're curious, here's how you would handle that if it's not true. So if you're like brains locking up because you can't stand the idea of treating a person as a point mass, you could do part F. I did it too. All right. So let's clear this out. We're going to start using this. In the first case, it's going to be I1 omega naught. And in the final case, it's going to be I1 plus I2. You might be saying, wait a minute, why isn't the person's moment of inertia there? A point mass at x equals 0 has no moment of inertia. So the person starts out with no moment of inertia. All right, so hopefully that made sense. Let's go look at the solution right here. Okay, so we get the person plus the disk and the person plus the disk. Initially, the person is 0 because they're at the center. Initially, afterwards, the person is mr squared. The disk isn't changing. Rearrange it, piece of cake. To make this plot, you shove it into Excel, but hopefully you at least said, when this is equal to 0, notice, if this is 0, you should get omega naught. So this is omega naught. And then as radius gets bigger, it's going to fall off in some weird way. This function actually relates to one called the witch of Agnesi, if you're into math functions that have names. No, Jay, but I was telling somebody in office hours, yes, so R, Joy, let me get the questions in order. R is the radius of the person from the center. So if I could go back, R is this radius. The person is walking outwards, and so at some instant, they are radius R from the center. Is that good? Yep, and then, okay, cool. Yes, that is incorrect. And so do you agree the person is not at capital R? Only when the person gets all the way to the edge would that be true. All right. Yep. Good. Good. Subtle. Subtle. And so notice here it says the person is distanced lowercase r. Yep. That's another way to do it. Okay. Good question. And then so Jay, Excel is not going to be on the exam, although it's used in your career, your life, and in general. This is what I have found. There are things I have learned about physics problems at much greater depth by plotting them. So if you actually want to learn your physics, making the plots is huge. Also, if you get in the habit of doing it now, you get faster at it. And in Physics 163, I make you draw plots by hand. So learning how to draw plots is something that you will be tested on in Physics 163, multiple exams. And you gotta do it. Sketching it is good, right? You could try and do that, but you'll get so much more from making the plots in Excel. All right. So if you have the time, I think you're crazy not to do it. You'll just be a much stronger student. And let's face it, that's something that's a job skill, not this stupid problem. Yeah. So yeah, think of these problems as excuses to learn other techniques. All right. Like coding, like Excel, or organizing, or being neat. All those things matter to your career. This particular problem, who gives a shit? All right. All right. So sketch that. And so notice this is where I gave the numbers. Okay. So notice here, these units don't make sense. This is also foreshadowing. So all I'm doing is I'm saying ignore units. And that makes it much easier to make the plots. So and this is a trick you might remember, if you try to understand the shape of a curve, set all the constants in that curve equal to 1. So if you set this to 1 and this to 1 and this to 1, right? Then it's just 1 over 2 r squared plus 1. It's a lot easier to plot that function. And I'm going to check everything in the chat and see if you're getting that. Oh, more lag. Okay, my bad. My bad. All right, make plots, ignore units, set the constants to 1, and that will get you that. And Phil, I'm sorry about the lag. All right. Nah, it's probably Napomo. All right. Now look at this one carefully. The rotational energy of the person has a max value of this. All right, try and do this one. Let's see. Let's take a look at it. Oh, go ahead. Ask your question there. I hear someone. I'm going to resist the urge to give it to you. Whoops. Try and do part C right now, okay? Try and do part C without looking at the solution. I want the rotational energy of the person, and I want the maximum value. Think what you would do. Maybe don't do it all, but think, what should you start with? What steps will you take? Maybe sketch it out a little bit, and then I'll show you the solution and tell you something you might find interesting. Okay. I'm going to let you do that. Apologies for me just sitting here. I'll wait 2 more minutes and then I'll start talking. Okay, I got a clock going. All right. So if I didn't give you enough time, I'm sorry. But again, we're just trying to, it's just so weird in this environment teaching like this. So I'm trying to do the best I can to simulate. I'm going to remind ourselves of the question. We're trying to do this one. Show the rotational energy the person has this maximum value. So rotational energy, hopefully the first thing you thought was 1/2 I of the person, omega of the person squared. And then you just say, well, this is omega, shove it in there. And then that's equal to, I'll just call that the rotational kinetic energy. I'm just going to call it K, okay? So then you could take dk dr, that's pretty sloppy there. Take dk dr and set it equal to 0. And then hopefully you thought, okay, solve for R, and then plug that in to right here. And then that gives you this number, which is this. All right. It's kind of circular there. I'm going to pause for a second. I'm not sure what you mean, Jay. If you want, you can unmute if you want to ask. I'm just not sure what you mean.
Okay. So I figured out that the RKE, the rotational energy, is equal to 1/2 of the I of the person times omega squared. And so then I just plugged omega and the R in. But I
Which R?
The R that you put down there. So I took my little R.
Yeah. Well, so the part of it was you're supposed to show that. So when you see a physics question that says show, that means you have to show that this is true before you can use it to get that.
Oh.
And this is how you figure that out right here. So that's what I was hoping you would recognize.
Okay. Thank you.
So, because on an exam day, obviously I wouldn't tell you the answers, right? So it's basically, I don't know why physics teachers do this, but some problems, they just tell you that way you know what the form of the answer is supposed to look like. And I think that's why because sometimes you're like, what does he want us to do? All right. Does that address that, Jay?
Yes, I thought you only wanted us to show max value equal to the 1/16. I didn't realize you wanted us to also show that little r is equal to that.
If you plug this in, that's cool, and you could get this, but then you have to still verify that it's a max. So the only way to do that is by doing this process. That's how you would show that it's a max, right? Is that good? Jay, you're good?
Yes.
Okay, well, yeah. So sorry about that. My bad. That wasn't very clear. On a test, it would be more clear because you just say determine the rotational energy of the person, right? So maybe I should take that out, and that would make that trickier for people. What do you think of that? Maybe I'll just say determine. All right. So now I know this is going to sound a little bit strange, but okay. So if you're sitting in here, just give me a second here, and then and let's I want you to respond in the chat right now, and I want you to respond with a number. And this is what I want it to mean. I want you to just tell me how comfortable you feel with that problem. 1 being not very comfortable, 5 being this problem was trivial for me, and then just okay, 6. Yeah, just be serious for a second. I know it's hard with physics. Parts A through C. So just tell me how you feel you responded. Like 3 is kind of like I got some parts, but I didn't get others. Or 4 would be like I could see how to do it, maybe I didn't do it, and 5 would be I got it. All right. Okay. All right. So I appreciate that, everybody. So here's the deal. Oh, sorry. 1 to, yeah. Okay. Yeah. Gotcha. Okay. Good. I love the sig figs, Joy. Good. Not 4. Come on. The reason I point this out, I like to tell students at this point, I stole this question from an MIT practice test. All right. And so I just want to point out, you can do the same stuff that people at MIT can do. You are just as good as they are, even though you're going to lowly Hancock College, all right? If you work at this, you can crush it. So just know I've been kicking your butts all semester trying to get you up to the same level as anybody anywhere in the world. Okay, maybe you're not there, but you're in the top third of the world. All right. If you can do all this stuff. So if you work at it, no, do not underestimate your abilities. It just takes practice. And we have had students go to Stanford and do well and get papers published in a summer internship. We have had students go to Carnegie Mellon or schools out in Cornell or Berkeley or anywhere you want to go. You can do this. It's just a matter of doing the bullshit. If you put in the work, you will do it. All right. And so it's a lot more dramatic when I go around the class and most people get all 3 parts. And then I'm like, well, you just did an MIT problem. All right. So, yeah, that's right. So if you just work hard, you can do this and you will get anywhere you need to go. And your level is getting there. All right. By the time you finish this course, you can learn any physics if you really had to. Hopefully you don't have to, but yeah. I like physics, but I know not everybody else does. All right, all right. This is a good time to take a quick break. So I'm going to